Hello viewers, welcome back to the course on matrix computation and its application. So today in this lecture we are going to discuss very important results based on the linear algebra. So in the previous lectures we have seen that for a given matrix A of m cross n dimension, then we have seen that this matrix is associated with 4 subspaces and these subspaces we can make like this one. Suppose this is, I will let you know that why we are making of this type, and the common point is just one point, it is intersecting, and another one I can represent the same way. Maybe I can write like this one. So these are the 4 spaces that is associated with this one. Now I know the matrix A can be written as a linear transformation. So it is the, so this I write column space of A, and this is also we write as a range space of A. So I can write the range space of A as a column space of A. Now this is, I know that the null space of A transpose. Now this one I write the null space of A, and this is I am writing the row space of A, then this is also equal to, I can write as null space of, the range space of the range of A transpose. So I can write this as a, in the short form, row of A. So it is a row space of A, and the point of intersection is this one. So we are going to show that these subspaces are orthogonal to each other, and we are also showing here, because this is a matrix is from of dimension m cross n. So it goes, m cross n is a linear transformation from Rn to Rm. So if I know that if it is a row space, the range is R, so that is the rank of A, and this is nullity. So suppose this is nullity, then I know that the dimension, so maybe I can write not like this one. So I can write here that let rank of A is equal to R, and that is also equal to rank of A transpose, and suppose nullity of A is some P, then I know that R plus P that is equal to n, that is a rank nullity theorem. Okay. So if I can say that if the dimension of this one is this one, so it's, if its rank is R, then its rank is R, then this is of dimension m minus R, and nullity will be of dimension n minus R, because this is a R. So this is basically Rm and this is basically Rn. So that thing we know from this transformation. Now from here we want to show a very important result is that, so the first result I want to the first one is the null space of A is perpendicular, is orthogonal to row space of A. So, we can write that is the null space of A is perpendicular to the row space of A, and the row space of A I can write as the range space of A transformation. So, this is the first one. Second one is that the column space of A, that is I can write, so the column space of A is orthogonal to null space of A transpose here. So, it means that column space of A is perpendicular to the null space of A transformation. So, these are the two results we want to discuss here. Now, so for this one I just want to write a definition. Two subspaces, say S and T. So, two subspaces, that is S and T, are said to be orthogonal to each other if every element of S is orthogonal to every element of T. Then only we can say that these are orthogonal. So, in this case we know that these are the subspaces, because null space is a subspace, row space is a subspace. So, these subspaces are orthogonal to each other, means each and every element of null space is orthogonal to each and every element of row space. Similar case is here. So, let us prove this one. Proof of the previous first. So, this is first I want to discuss that the null space of A is orthogonal to the row space of A. Now, let suppose we have A x equal to 0. So, this is my A, that is m cross n. Okay. So, this is, I know that this is A is m cross n and x is n cross 1. So, that is equal to 0. So, if this is equal to 0, it implies that x belongs to null space of A, because it is going here. Now we have A x equal to 0, this is we have. So, A is basically, if I write the A, if you see from here, then this is R1, this is R2, Rn, and this is my x. So, it is x1, x2, xn, because x is coming from n cross 1. So, nth dimension, and this is m cross n. So, m number of rows and n number of columns, that is equal to the vector 0 0 0. Now, if you see from here, then what I am doing is that we are multiplying this vector with the first row of the matrix, and we are getting 0. So, from here if you see that I can write from here that R1 dot product with x, because this is my row vector and this is my column vector, and I am taking the dot product, that is equal to 0, or maybe I can write this as directly the matrix form. So, I can write R x that is equal to 0, because it is a row and the column. So, it is just the matrix form I can write. Also R 2 x that is 0, R 3 x that is 0, and R n the last one. So, this is my m, because we have a n number of rows. So, it is go up to m. So, that is equal to 0. So, from here you can see from here that I can say that the R 1 is orthogonal to x, R 2 is orthogonal to x, R 3 is orthogonal to x, and so on. R m is orthogonal to x. So, all these rows are orthogonal to the vector, and this vector lying in the null space of A. Now, we are able to see this one, but as we have seen there that we are able to tell that two subspaces are orthogonal to each other only if the each element is orthogonal to the each element of the other subspace. Now, so let us take any element. Now, for any element in the row space of A. So, if I take any element in the row space of A, that element will be spanned by the rows. So, that element will be a linear combination of the rows. So, if any now for any element in the row A is written as can be written as C1 R1 plus C2 R2 Cm Rn, because it will be the linear combination of these rows. Now, I take this element, it can be any element, and I am taking the dot product with x. Now, from the definition of the dot product, I know that this will be equal to C1 R1 taking the dot product plus C2 R2 taking the dot product and Cm Rm taking the dot product, and this value we already know that this is equal to 0 0 0. So, that is equal to 0. So, from here I am able to see that any element from the row space taking the dot product with any element x from the null space is giving this value 0. So, which implies that every element in row space of matrix A is orthogonal to every element in null space of A. So, which implies that the null space of A is orthogonal to row space of A. So, this is one of the important result, and from here you can see that the common element will be only the 0 element that will be lying in both the subspaces, because it is the subspaces. So, 0 element will also lie in the NA and 0 element is also lying in row space of A. So, that is why in here we are writing this connecting with the point. So, this is the 0 element, 0 element of Rn. So, that is the 0 element of Rn, or maybe I can write it with some another color, maybe I will. So, Na of dimension n minus r, and this point is 0 element of Rn. Similarly, this is also 0 element of Rn. So, they have only one point common to each other, that is just the 0 element of this one. So, we are able to prove the first part of this one. The second part is the column space of A is orthogonal to null space of A transpose. So, second one, we need to show that the column space of A is perpendicular to the null space of A transpose, because both are lying in the Rm, they are the subspaces of Rm, and Na and row space are the subspaces of Rn. So, this one we want to show. Now, it can be clearly proved that now for any system Ax equal to 0. So, that was just now we have proved. Now, we can take transpose of matrix A. So, that is A transpose. So, I will not take this system. Now, we take the transpose of the matrix, then A transpose y, then let I take the system A transpose y equal to 0. Now, from here it implies that y belongs to the null space of A transpose, and also row space of A transpose is perpendicular to the null space of A transpose. Just now we have showed that in the previous one that the row space of A is perpendicular to the null space of A. So, the null space of A transpose is perpendicular to the row space of A transpose, and also we know that row space of A transpose is same as column space of A, because I am just taking the rows as the column in the transpose. So, row space of A transpose, that will be same as the column space of A. So, which implies that null space of A transpose is orthogonal to column space of A. So, they are also orthogonal to each other, and then the point of common intersection is only the 0 element. So, this is the results we want to show. Now, one more thing we want to discuss about. So, now we want to discuss about the matrix. Suppose we have a m cross n dimension, then we want to discuss about A transpose A, this matrix, because in this case what we are doing, that suppose I have a matrix A. So, A matrix is basically row 1, row 2, row m, that is m cross n, then if you see from here, A transpose A is basically, now the first row will become the column, R2 will become column, and Rm this one. So, I can write this as R1 transpose, or maybe I can write here, if R is the row, then it will be column. So, I can write here R1 transpose, R2 transpose, and Rm transpose. So, if it is of m cross n dimension, this will be n cross m dimension. So, basically this will be A transpose. So, if A is this one, the A transpose will be this one. So, basically I can write this as directly from here, no need to write this. So, this is my A transpose. So, from here if I want to write A transpose A, so what we are doing here is that I am taking my R1, R2, Rm, and this is R1, R2, Rm. So, this is my A transpose A. It means that I am multiplying, I am taking the dot product of each and every rows of the given matrix. So, now I want to discuss about some properties of A transpose A. So, properties of A transpose A. So, first thing is that A transpose A is a square matrix always, because if A is A transpose will be n cross m and A is m cross n. So, it means that A transpose A will be n cross n. So, that is always square matrix. Second thing is that A transpose A is a symmetric matrix. Here we are taking all the real valued spaces. So, that is why we are dealing with the transpose only. So, it is a symmetric matrix because A transpose A, I can write transpose. So, this is A transpose, A transpose. So, this is A transpose A. And third one is, we have already discussed that A transpose A is positive definite matrix. So, it is very difficult to construct a positive definite matrix, but if any matrix is there, we can write A transpose A is a positive definite matrix, and we have proved this earlier also. So, positive definite matrix means all eigenvalues are positive. Now, how we can show this one? So, this one I can write, let I write the, so A transpose A, if I take x, that is equal to lambda x, and from here I can write that I just multiply by x transpose. So, A transpose x, x can be written as x transpose lambda x, where lambda is the eigenvalue, and from here I can write that lambda will be x transpose A transpose x x transpose x. Now x is a vector, so x belongs to Rn. So I know that this can be written as x transpose over square, because this is just the magnitude square of the vector x. Now from here I can write this lambda can be written as, again I can write this as a x transpose, because if I take the transpose it will be x transpose A transpose, and then I can write from here, this is not x, it is A it is A, it is A. So I can write this as a AX. Now we know that this AX is again the vector, so this can be written as, I can write this as a AX the magnitude square, this one, and this is the magnitude or the norm square, so this is always greater than or equal to 0. So from here you can see that, so which implies that lambda is always greater than or equal to 0. So it is positive definite. So it will be the positive definite matrix, and this will be 0 only when this part Ax equal to 0, otherwise this is never equal to 0. So after showing this, that this is a positive definite, we want to discuss another important result. So this is the third property. So the fourth property I want to discuss is that the null space of A transpose A is also equal to null space of A. That is, I want to discuss this. So this one I want to discuss, because null space of A is the subspace of Rn, and this is also A transpose A is a n cross n matrix. So null space of A is also of the dimension subspace of Rn. So I want to discuss that this is the equal. So let's do that one. Now let us take A transpose A x equal to 0, or maybe I just take, let us assume x belongs to null space of A transpose A, which implies that A transpose A x is equal to 0. This one I can write as A transpose A x equal to 0, and from here I can write that if A transpose A x equal to 0, which implies that A x belongs to null space of A transpose. Now, so this is belongs to the null space of A transpose. Also we know that Ax belongs to column space of A, because Ax is just, what is that? It is the span of the columns of A, so it belongs to the column space of A. But so this is also belongs to column space A, and this is also belongs to the null space of A transpose. null space of A transpose, just now we have seen that it is orthogonal to the column space of A. This is we have seen. So, which implies that, so now Ax also belongs to the null space, Ax also belongs to this one, but this is orthogonal to each other. So, orthogonal to each other and the common point is only 0, which implies that my Ax should be equal to 0, because only intersection point is the 0 of that space. So, that we have seen. So, which implies it should be 0, and from here I can write that the x belongs to the null space of A. So, that implies that I have taken the element from the null space of A transpose A, and I showed that this belongs to the null space of A. So, it is a subspace of this one, subset of null space of A. Now, we can go directly the converse also. So, conversely very easily we can do that, we take the element from NA and going the same way. So, conversely we can show that null space of A is a subspace of null space of A transpose A. The same way I will take the element from this, I will reach here, then from here I will reach here, and we will go back from here. So, from these two we can show that the null space of A transpose A, that is equal to the null space of A. Also, so after doing this one, so null space of A and null space of A transpose. So, from here I can say that nullity of A transpose A is same as nullity of A. This is we are able to make from this. Now, so after doing this one, I want to, so this is the fourth property. So, I want to discuss the fifth property. So, the fifth property is that the rank of A transpose A is same as rank of A. This one I want to discuss. Now, we know that since now we know that this A is M cross N and A transpose A is N cross N. Now, using rank nullity theorem, I can say that the rank of A plus rank plus nullity of A is equal to N. Also, rank of A transpose A plus nullity of A transpose A, that is also equal to N, because A transpose A is n cross n dimension. So, it is a subspace of Rn. So, the rank will be rank of A transpose A plus nullity of A transpose, that is also N. Now, from here, from these two, but nullity of A transpose A is same as nullity of A, that we have seen here. So, if I have these things and this is all N, so which implies that a rank of A transpose A is equal to a rank of A. So, this one can be proved by this way. So, it means the nullity of A transpose A is same and the rank of A transpose A is same. Now, so after doing this one thing we also discuss is that now we want to discuss that this A transpose A is a square matrix, then we want to discuss that when this matrix is invertible. So, this one we want to discuss because it is a square matrix and we found that the rank of A transpose is equal to the rank of A, then how we can say that this matrix is invertible or not. So, this one we can find out that when we can say that this matrix is invertible. Now, so let us take example. So, this will see with the help of example. Let us we take the example. Now, suppose I take a matrix A having, suppose it having 2 columns. So, let us take the example I take 1 1 1 and another is 1 minus 1 2. So, this one I am taking. So, this matrix I have taken here. Now, if you see from here, then these vectors, so first column the second columns are linearly independent to each other. So, I can say from here that rank of A is 2 in this case, because the first column and the second column are linearly independent to each other, that we can verify very easily, that this vector cannot be written as a scalar multiple of this vector. So, in this case the rank of A is 2. Now, if I take A transpose A, so this will be 1 1 1 1 minus 1 2 and this will be 1 minus 1 2. Now, from here we know that A transpose A is just taking the dot product of the rows with all the rows. So, this is first with first, so it is 3. Now, I am taking this with the second row. So, I am taking 1 minus 1 2, so it will be 2. Then this is again 2 and this one I am taking 1 plus 1 2 plus 4 6, and this is of course 2 cross 2, and also we know that rank of A transpose A here, if you see from here, this is coming 2 because they are not scalar multiple of each other. It is 3 2, it is 2 6. So, if I multiply by 3 here, so I cannot get second row with the first row, and also from the previous this one I know that the rank of this is equal to this. So, it is a full rank. So, now from here I can say that this is a 2 cross 2 matrix and rank is 2. So, from here I can say that the matrix A transpose A is invertible. So, I can take the inverse of this one. Now, if I take the matrix A as 1 1 1 and I take 2 2 2. So, in this case I know that the second column is 2 times the first column, and from here if I solve this one in the echelon form, then I can find that the rank of matrix A is just 1. So, in this case just rank is 1. And now, if I take the A transpose A, so this will become, because I am just multiplying with its row, so it is 3, then it will be 6 it will be 6, and this will be 4 plus 4 plus 4, it is 12. And you can see from here I can write this as 3, 6, and just it is a 2 times of 3 and 2 times of 6. And now the rank of A transpose A in this case is 1. So, from here I can say that A transpose A is not invertible. So, when the given columns are linearly independent, then A transpose A is invertible, and when they are linearly dependent, then the corresponding A transpose A is not invertible. So, that things we have to keep in mind. So, let us stop here. So, in today's lecture we have discussed about that the 4 subspaces associated with the given matrix, they are orthogonal in the sense that we have shown that the null space of matrix A is orthogonal to the row space of the matrix A, and the null space of A transpose is orthogonal to the column space of the matrix A. And then we have discussed the another important matrix, that is A transpose A, and discuss its few properties. In the next lecture we are going to use these properties to discuss a least square solution. So, thanks for watching. Thanks very much.